just going to go over some of the, this thing gets moved a lot. Go over some of the things that we haven't covered. And then we'll start a different section. We'll be starting section 7.8, which is improper integrals. If I haven't mentioned it to you, on Wednesday of next week, it's a holiday, I believe. So that means we only have 4 days. And the fact I missed a day didn't help. So we will not, the schedule says we will be doing a section, I think it's 8.4 off the top of my head, 8.3 or 8.4, which is to do with applications. And I'm not going to be able to do that next week, so we'll push that onto the next week. So your test, I know you just finished one, but give you a heads up, you got a whole week to go again, but the next test won't include that for that reason. And also the next test won't include tables. So the next test will only have 3 sections in it. Okay, so what are the kind of finishing off things that I believe we need to look at? And this is a version of question 10. I'm not going to do the whole question. I just want to show you what they're getting at. Well, let me get that 2 then. 2 to 618. In question 10, they went to say, find the arc from the point, the arc length of this curve from the point P to the point Q. That guy there, right. Oops, somebody just came in. Now we know what the formula is. Since this is obviously x's, it's going to be the integral from somebody to somebody. Well, that's the first issue. Normally you get things like this, don't you? So you know to start at 0 and finish at 4. In this question, it's from 2.2 to 6.18. What are the limits of integration from here to here? What values of x do we use?
2 to 18.
2, yes, 2,
6.
The x coordinates, right? I don't really need to know what the y coordinates are, and in a way they're kind of distracting, aren't they? So if you get an arc length from one point to the other and you're using x's, you use the x values, right? 2 to 6. You then set up the integral, which goes something like this. 1 plus the derivative of this guy is x, and then you square it. Okay, now, how do you think you're going to integrate this guy?
You could split up the radical and then use the power rule.
You're not allowed to call that 1 plus x. I wish we could. That would be a good thing if you could.
Could you use an x sub? Like,
yeah, you could use an x sub, or you could use
Table?
Right. Now, for a test, you will use x subs, so you get lots of points. But for homework, wouldn't it be probably quicker to use the tables? So you go hunting for what that guy is, and then you plug in x equals 6, take away what you get when x equals 2, and call it good. Okay? That makes sense? So, yes.
I'm not sure, like, if you were to do an, sorry, never mind.
You got it? Okay. So, but as I say, for homework purposes, you probably want to use the tables because would you agree they're a lot quicker. Essentially, what the tables does is tell you what the answer is, right? And then you just plug in some x's. So that's kind of that one looked at. Now, it's question 11. And we have an x squared equals y take away 4 cubed. And the point P is going to be 1, 5. And the point Q is going to be 27, 13. And I know we're going to get the arc length, and I know it's an integral, and it's a square root of 1 plus somebody, and then it's going to have a d. So let's look at the clues here. The way this question is written, do you think this is going to be a y equals f of x, or is it going to be an x equals g of y? What kind of situation are we looking at here? Agreed. So to get an x equals, you would have to take, well, half the power would be the way I would look at it. And I would call that guy g of y. So it's going to be 1 plus whatever the derivative of that is squared. And you may, there's no real shortcut for that. You're just going to do some algebra and some nice things will happen. I'm not sure of the numbers, but I'm pretty sure I know what it's going to end up being. It's going to end up being something like 5 plus 3y or something, or 5 plus y, which is not a hard thing to integrate, right? It'd be a u sub. But one last piece of the puzzle. Since we're doing it with respect to y, don't we need a start and a finish value in terms of y? And it's the same kind of situation up here, but with one change. Isn't it the y values? (5) and 13 that we use. Be comfortable with those? They're still arc length questions, but they have the little idiosyncrasy of not telling you the start and finish. And they don't necessarily even tell you which of the two flavors of the arc length formula are most suitable for that situation. But typically, if you can see a y equals function of x, won't you go this road and use x's? If you see something that's close to, even if it's not perfectly the same, but an x equals something like here, won't you go the x g of y route, which would be this one? Are we good? Can I move on from here?
For doing that problem, would it be the same, like you would either do an x sub or use the table?
Yeah, you probably do a u sub later. Yeah.
Oh, not an x sub?
For this one, I think the math comes out and it ends up being something like 3 plus y. So the square root of 3 plus y would be a u sub. You'd use an x sub if there was, I don't know, 3 plus y squared, that kind of look. Have you noticed that all the x subs have a y squared in them or an x squared in them? It's always x squared minus 9, x squared plus 9, 9 minus x squared, right? X subs have squares in them. If it's just linear, 5 plus x, 5 plus 2y, then it's a u sub, right? We're good? Good questions. Right. So the last piece of this is called the arc length function. So let me show you what you're doing, and you'll see that it's not that big a difference. You've kind of, how to do 3/4 of it already. So we'll show you how it works. Suppose you have a function from here to here. And this guy here is a, but this guy here is x. And you're trying to find the length of the curve from a to x. So the arc length is the integral from a to x. And then you go 1 plus f dash t squared dt. Now you could do that. Would you agree the integral, the arc length from a to b would be a to b? Well, the arc length from a to x, wouldn't it just be a to x? Now we have a top formula that looks like this, and we have a different looking one that looks like that. Why do we use that top one and not the bottom one? Why do mathematicians tend to think writing it this way is better math than writing it that way?
Because X is one of the values that's going to
Yeah.
evaluate it.
Yeah. It's kind of bad math to have a variable that's also essentially a constant, right? A replacement value. So just for math purposes then, and to keep things kind of mathematically valid, we use this version. You can't use this version really, because what you're saying is that this guy and this guy are the same, but technically that's a variable and this is a constant value. So far so good. So what does it look like? Well, you'll get a function and you'll be asked to find its arc length formula or arc length function. So where's my first one? Here is the function. It's going to start at the point 25 to 50. Okay. Now its arc length is going to be the integral from some start number a to x of the square root of 1 plus f dashed of t squared dt. Right, that's the formula we're going to use. Oops. This fella, oops, is going to be called s of x. Since this is your starting point, that's like where P is. What will be the x value here? What shall I use?
25.
So it's 25 to x, the square root of the x. Now, although that is the function, we think of it like that. Okay? So 1 plus its derivative squared. Okay, if you differentiate this, don't you multiply by the power and you reduce the power by 1, which gives you that guy. And this fella then becomes the integral from 25 to x of the square root of e. Well, you double that and you get 1 plus 2/3 t to the negative 2/3. I'm just going to put a dot, dot, dot on that.
Don't you square the coefficient too?
Thank you. I'd say go hunting for tables. Right, if you don't like the looks of it and you know there's nothing like a U sub going to save you, you're probably looking at an X sub or tables. But in homework, don't we go for tables rather than X subs, right? And I don't think there's an X sub in the world that's going to save that either. So this is definitely a table candidate. So let's do one that actually I can take to the end. So this is question 12. The function is 2x to 3/2, and the point is 1, 2. And I want to find the arc length function. So it's going to be the integral from 1 to x, the square root of 1 plus the derivative of that function squared in terms of t dt. So if you think of that as being this fella, then we get an integral from 1 to x. Okay, if you differentiate the, oops, this thing's never quite where I need it to be. It's got a kind of bounce thing there. There. Okay, if you differentiate this, right, it's power rule. Multiply by the power, reduce it by 1, and you will get t to the half. You'll get 3t to the half squared. So it's going to be the integral from 1 to x, the square root of 1 plus 9t dt. Okay, now we're taking this one to the end, so I'm not going to say, oh, use the tables. Actually, you could use a table in this, but I think it's better not to. Any suggestions how I integrate this? Don't worry about the 1 in x. If you wanted to integrate this square root, what would be a good strategy?
U sub.
Agreed. And the u sub would be what?
1 plus 9t.
And so the derivative would be 9. The crossover would be that. And instead of isolating a dx, don't we now just change it and isolate a dt? That's essentially the same process. And what do we now get? Well, we get the integral of the square root of u 1/9 du, which becomes the integral of 1/9 u to the half du. Everything looking good? Okay, would you agree this is a power rule? Great. So what do? We take this guy and we add 1 to the power, and then we divide by the new power. That gets me what? 2/27. This guy is the square root of u cubed. That's what 3/2 looks like. And this guy now looks like 1 plus 9t cubed, evaluated at t equals 1 to t equals x.
Small question. We're using a u sub just because 9t doesn't have a square above it, right?
Yes.
Okay.
If it had a square, I'd be looking at x subs or tables. So what does that get? Okay, well, it gets me 2/27, the square root of 1 plus 9x cubed. Take away, well, if you plug in 1 here, you get 10. 10 cubed gets you 1,000, so it gets you 10√2. Yikes. 2 times 10√10 over 27. I didn't say the answer was pretty. I didn't predict it would be pretty. But that's the answer. So can you see that it's kind of 3/4 what we've been doing, isn't it? It's still an arc length question. And the major differences is that things are now in terms of a new variable called t, and that one of the limits of integration will have an x in it instead of a typical number.
Is there not a
And
plus
your
C?
result then ends up with x's because of that. Matthew?
Is there not a plus C?
No, technically not. And the reason why there's not is because it's got limits of integration on it. Even if though one of them's an x, if you have a limit of integration, plus c, it doesn't matter. Because both of them would have a plus c and they would have cancelled out. I see puzzled looks. I hope that's just thinking looks. Are we okay with this one? Right. There's just one last one of these I want to show you, and that's essentially going the other way. So let's see if I can find one. Okay, I'll just make mine up then. Suppose you had x equals, I know what should we do? Sine of y. And it was going to go from the point P 0, 0. Then our formula would be technically s of y, because this is a y fella. The integral from 0 to y of the square root of 1 plus the derivative of this guy, which is cosine y, squared dy. So it's from start number 0 to y of 1 plus the derivative squared. In this case, it's the integral from 0 to y, the square root of 1 plus cos squared y
Can it
dy.
be
Is it not t?
Oh, darn it in space. That proves that you lot are paying attention, which is good. So it ends up being that guy. I'd have to use tables in that. Would you agree? There's not an algebraic way that'd get me out of trouble. So I'm assuming that you'll find a table for the square root of 1 plus, well, it'd be called 1 plus cos squared u, won't it? Because the tables always use u. But you should be able to find something. Unless I just randomly generated an impossible question, which is actually very easy to do. But at least you know the process. Are we good? Right, now, the last part of that I think we've covered. The last few questions only ask you to set it up. In other words, they ask you to get to, oh, I've got a question handy. They ask you to get to there and stop. So I guess I could do one. These are easy to make up. This is us back to the normal world, right? F of x is equal to sine x plus cosine x. And we're going to do it from 0 to pi, right? Now the arc length would be the integral from 0 to pi square root of 1 plus the derivative squared dx. And the derivative of this guy is cosine x, and the derivative of this guy is negative sine x. And we have just finished this question. Because
in this
they
case,
say
we wouldn't have to do t?
we don't need t's or anything. In this question, you're given a start and finish value. If it's
Okay,
going to
I see.
have a t, it's going to say the arc function or the arc length function. They'll use terms like that. These questions just say, let's get the phrasing. Find the arc length. No, set up there. That's the phrasing. Set up, but do not evaluate the integral for the arc length. So, would you agree I've set it up?
Yes.
That's it. So in a lot of ways, that question is going to be much quicker, isn't it? Because you don't need to do any algebra or trig identities or anything, because you don't need to evaluate it. Only set up what it would be if you were going to try and do it. So don't overthink those questions, right? Don't spend a lot of time doing a style point on it, you know, making it look pretty, trig identities, all that stuff. And the reason I'm saying don't do that is because you don't need to if they just say set it up. Now, on the other hand, if they wanted you to get the answer, right, they needed to know it as an exact value, then you'd have to do trig identities and, you know, all that fun stuff, and you know, and figure out what it is. I got nods on that one. That one I think worked a lot nicer, right? Because there's not really that much to do. So we are going to start today, and we won't get it finished because there's tons in it. Topic called improper integrals. So we'll finish it, I hope anyway, we should finish it on Monday. And then that'll give us Tuesday, Thursday, you do the applications. We'll probably get started, but we won't be putting the other, rephrase that. We will do this today and we'll finish it on Monday. On Tuesday and Thursday, we will do surface area. And then we should get started on Friday with the applications, but that won't be in the test because we won't get it finished. And it won't be in the homework. Right, so let's tell you what an improper integral looks like. There are two types. Very often called type 1 and type 2. For the life of me, I can never remember which one's called type 1 and which one's called type 2. So I have a 50-50 chance of giving you the right name. It won't really matter because knowing what it's called isn't as important as knowing how to get the answer, right? So I believe, only 50% sure, that a type 1 looks like this. One or both of the limit of integrations will be infinite. So the integral from 1 to infinity of 1 over x squared, right? That would be an example of an improper integral, type 1. I'm not quite sure why it's called improper. Improper sounds to me like there's something wrong with it. I guess there is something wrong with it, right? Infinity is not a good number, right? So I guess there's something wrong with it. Okay, I take it back. I think that's not that bad a name. Now, type 2, I'll have to show you an example of it. What's the problem with type? That should be an X. Let's say it's 9. What's wrong with type 2? What's improper about trying to get that integral?
Can't divide by 0.
When you, yeah.
Right. Doesn't it have what you would call in 141, what I would call today as well? Doesn't it have a nasty thing called a vertical asymptote at 3? So improper integrals are essentially integrals where infinity is involved. Now, it might be infinity is involved because it's one of the limits of integration. It may be infinity is involved because 1 over 0 is a bad idea, but visually isn't 1 over 0 a vertical infinite asymptote, right? So to be able to find either of these two kinds, right, we have to do a little bit of sneaky algebra. So hold the thought and let's look at how to find limits. So we're going to do some skill building on how to find limits, and then we'll come back to how you do these questions, because these questions involve limits, right? So I want some practice at that. So what's the limit? And I'll use the variable t as t tends to infinity of 4 over t cubed. That's our first one. We can get some limits at infinity, like this limit, for instance. We can get some limits at infinity by what I call the brute force method. Essentially, you use infinity like it was a number. And wouldn't this be 4 over infinity cubed? And what does 4 over infinity cubed look like? It's a physical number, What is 4 over infinity cubed?
0.
0. Now, if you get 4 over t or 4 over t squared, or I'll put one more in. If you get the limit as t tends to infinity of 4 over the square root of t, won't you get 4 over the square root of infinity, which is 4 over infinity, and doesn't 4 over infinity get you 0? I call that the brute force method. Essentially, you look at the variable as if infinity was a number, and you can do some calculations, very, very limited calculations, but you can do some. Let's do brute force. What will 3 infinity squareds get you?
To infinity.
And typically when you get an answer that's infinity, right, we are going to use a very special word. We are going to say it's divergent. So we won't even mention infinity. We won't say the answer is infinity. We'll just say that the integral is divergent, right? So the infinity is what makes it divergent, right? But we don't use infinity. So far, so good. Let's do a brute force on this fella. What would the natural log of an infinitely big number be?
Would it also be divergent?
Correct. Infinity. And we would say it was divergent. Now I'm going to give you a trick question. Here are two very similar, but they do have differences, limits. The limit is t tends to infinity of e to the t in both cases, but one t goes infinite and the other one t goes to negative infinity. According to brute force technique, you would get that, right? Now the big decision time. This is where the sneaky part comes in, right? Told you it's a trick question. Tell me the answer to either one of those.
0.
For which one?
The bottom one.
What's the answer to the top one?
Infinity.
Then you nailed it. Now, some of you might be puzzled where his 0 came from.
Because
Great.
it's 1 over e to the infinity.
Which makes it 1 over infinity, and doesn't 1 over infinity get you back to 0? Agreed? There's a puzzler. Any candidates? Any takers on this one?
Wouldn't it be 1?
Because
Because the unit circle can only go from like -1 to 1.
okay, why can't it be -1 then?
I don't know.
Or 0?
It is positive infinity.
No. It's got
Could
yous,
it
hasn't
still
it?
end up being negative though?
I don't think there's an answer.
Good. That might not seem like an answer, but it is the answer. There is no answer to that. If you think about the cosine function, doesn't it go like that forever? So where is infinity? Well, infinity is not like 42, right? It's not a real physical, this number is equal to infinity, right? Isn't infinity just saying, look, if you keep traveling like that to the end of the universe, what would you end up at? Well, the answer is for a cosine function, you'll end up, there is no answer, right? You could end up anywhere between plus and minus infinity, right? There is no fixed value. We also call those guys divergent. So do you see how the word divergent saves us having to try and figure out different ways of saying weird ones, right? Okay. Here's another weird one. Any takers on this one?
Infinity?
Yes? Do you want to tell me where how you figured that out? It is, you're right.
Because negative infinity squared is infinity.
Okay, so if we do a brute force thing, negative in squared infinity gives me that. Would you agree that 1 plus infinity squared is still infinite? And would you agree that the square root of infinity is infinity? Do you see the math with infinity is kind of weird? Infinity plus 1 is still infinite, right? Infinity squared is still infinite. Wouldn't a half infinity still be infinity? So you have to invent a slightly different weird math when you do any calculations with infinity. Let's try this guy out.
Professor, I had a question.
Say again?
I had a question.
Go for it.
So for when you evaluate limits, I think I talked about this in Calculus 1, but I forgot. How come you're able to plug in that number that it approaches to like evaluate it?
How can I plug in infinity?
Yeah.
I'm just thinking, what is the value of this expression going to be as t gets infinitely big? Right, that's what this means, right? All of these mean that. So all I'm doing is saying, okay, suppose t was a billion squared, the American debt, you know, and so on and so forth, getting bigger and bigger. And then I say, okay, suppose it was infinitely large. What would 1 plus infinity squared? It's just an abbreviation for 1 plus an infinitely large number squared. And the answer to that would be, you would get an infinitely large number. And what's the square root of an infinitely large number? And we know that that would be infinitely large. Now, if you don't see that, think about, what's the square root of a million? Well, it's 1,000. What's the square root of 10 to the power of 100, which is a Google? That would be 10 to the power of 50, right? You see, as it gets bigger, the square root is infinitely large as well. So it's a convenience to write down as if it was a number like 42, you know, to write down infinity as if it was a number, because it does allow us to come up with the answer, at least in these cases. Isn't the answer 0 or infinity, or it just doesn't exist, in which case we say divergent? Here is a trick question.
Does not exist.
And what word do we use when it don't have a number? We call it
Divergent.
Divergent.
divergent. You see how divergent is helpful, right? It just is a coverall. If it ain't a number, right? If it's not 1 or 0, if it ain't a physical number like a half, right? It's divergent. Okay. Of course, that's only the beginning. Let's look at strategies for fractions. Now, again, this is going to be a way back to Calc 1. Can you remember finding limits as x tends to infinity? This is just the same thing, but it's t tends to infinity, of a rational function. There were two specific techniques that we could use to find the limit to this. And it is a number, and the number isn't 0, right?
Isn't it 1/2?
It will be 1/2. So now we have to figure out a little bit more mathematically where that number came from. Now it says there's two techniques. One has a French guy's name, L'Hopital. You remember L'Hopital, right? That is very helpful when you're talking about sine t's and e to the t's and things like that. L'Hopital works really well with those. It will definitely work well with those. It'll just maybe take you a couple of shots at L'Hopital. In other words, you have to do it twice or even 3 times, but you'll get the answer.
Is that the derivative of the top and the derivative of the bottom?
Exactly. That
Okay.
is exactly what it is. And I'm going to do this question with L'Hopital first, and then I want to show you, because we only have 5 minutes left, the other method. Right, now according to L'Hopital, you put a little L above the equal sign, which is normally the convention that mathematicians use to say, hey guys, I'm going to be doing a thing called L'Hopital. And it becomes the limit as t tends to infinity of, just like you said, the derivative of the top, 6t squared, and the derivative of the bottom, oh, plus 1, and the derivative of the bottom is 12t squared. Now, if you can't get the answer by brute force just means you plug infinity in and you get a number, you just do L'Hopital again. And the trick about L'Hopital is if you keep doing it, you should come up with an answer as long as it's a question designed for L'Hopital. Now, if you differentiate the top, would you agree it's 12t? And if you differentiate the bottom, it's 24t. And very often in L'Hopital, especially when it's polynomials top and bottom, you'll eventually come to a point where these two guys may cancel out, or at least simplify. And can you see it's now the limit as t tends to infinity of a half, which is a half. Are we good with that? Now, if it's a polynomial on the top and a polynomial with L'Hopital, if you keep doing L'Hopital over and over again, you will eventually end up with 3 things. You'll either get that left, in which case the answer is 100, 8.5, or you'll sometimes get that, or sometimes you'll get that. Right, so what will that guy get you? What's the limit as t tends to infinity of 1 over 2t?
0.
0. 1 over infinity by brute force, 0. And what's t over 2 going to get you as t goes infinite?
Infinity?
Right? Because infinity over 2 is infinity, and we call that divergent, right? I said there were 2 ways. Let's show you the second way. Do you notice that these both guys have t cubed as the highest power? Whatever the highest power is, you divide the top and bottom by that same power. Now, sometimes one of them will be different than the other, like this will be cubed and this will be squared, right? or this will be 4 and this will be 2, right? So if there's a difference, you know, one in top's different than bottom, you still pick the highest power. So if there's a t squared and a t to the 4, you pick t to the 4, for instance. Now this divide top and bottom by t cubed. This is what this fella turns into if you do that. Divide this guy by t cubed, you get 2. Divide this guy by t cubed, you get 1 over t squared. Divide this guy by t cubed, you get 4. And divide this guy by t cubed, you get 5 over t cubed. Does this ring bells with you? Can you recollect doing this?
Yes.
Right. Now, one of the conveniences of this method is that you don't have to do L'Hopital 2 or 3 times. You only need to do this once, and you'll be left with an ugly looking fraction. What you then do is brute force. Turn all the t's into, in this case, infinite. So 1 over infinity squared and 5 over infinity cubed. Isn't 1 over infinity 0? So 2 plus 0 gets you 2 on the top. And isn't 4 plus 5 over infinity 4 plus 0, and that gets you 4? And then you get the answer, a half. Now, there are quite different ways to do these, right? L'Hopital is all about differentiating the top and bottom and then keep doing it until you get an answer. And this method is all about dividing the top and bottom by a particular power of t. And boom, you got your answer. Right, will you all spend a few moments saying hi? Because we're kind of reached the end of today. Have we? I'm not sure. This isn't new stuff, but we learned cool stuff. So coming back to you, L'Hopital and
Yes.
this fella, right? Now, depends who you got in Calc 1. I don't think anybody does L'Hopital differently, but there might be different nuances on this. Is this pretty much the way you were showing the setting method? Is that the way you were showing? Well, if you got me, it would be, right? But if you got someone else, did it look like this as well?
Mm-hmm.
Right.
Yeah.
So we'll be using this to find improper integrals eventually. I think I should do some politician jokes before we leave. You ready?
Yep.
How can you tell if a politician is lying?
I don't know.
But his lips are moving. Okay. What's the difference between a politician and a snake?
Nothing.
Almost. Some people like snakes. Okay, have a nice day, guys. I shall see you all on Monday. Try and keep up with the homework. You won't really be able to do anything on the improper integrals, but you should be able to do something on the other 2 sections. Okay, that's it. Bye-bye. If you have questions, do usual, hang about, and I'll go over them. Ah, you got a question today, Emma?
Yeah, I remember, well, during the test, I really struggled with one question, number
Okay.
7.
Have you got, could you tell me it off the top?
I got it in my notebook. Let me look.
Okay.
Okay, so it's the integral from 0 to a of 7x squared.
Ah, we'll start again. 7x squared.
And then the square root of a squared minus x squared.
Oh, I remember now.
Yeah.
Gotcha. Right. This question is long.
Yes.
Okay. So, first thing I'm going to do is that don't we have to do an x sub?
Yes.
And the x sub was a,
sine theta.
agreed. And so you differentiate with respect to theta, you get a cosine theta. And you do the crossover and you get that. Great. So
I
that
can't-
probably isn't where you went wrong.
I can't see what you're doing.
Oh, then let's make that visible, right?
Yeah.
Right. So as I was saying, I don't think that's where you would go wrong, because most people, that's not where they go wrong. Actually, we don't know what those are now because we've done a change of variable. It's going to be 7. X gets replaced by a sine theta. A squared, take away a squared sine squared theta.
Okay. I know what I did wrong. When I put in the x for 7x squared, I forgot the a. Oh my goodness.
Well, that was a quick fix then, right?
Yeah. Okay.
Okay.
I can't believe I did that. I slaved over this question. I don't know why. It took me a
Well,
really
one
long
of the hard things when you make a mistake is when you go back and look at it, it's very hard to see it because it looked right when you put it down. So it still looks right when you look at it a second time. But I wouldn't know because I never make mistakes, right?
right.
Okay.
I also missed 8 and 9, right? in a row.
Okay. What's the next one then?
So 8 would be the it's just the integral, you're not evaluating it.
Mm-hmm.
And it's the square root of x squared minus 25 divided by x cubed. And so that's another x sub
Which x sub should we
Five.
use this time?
5 secant theta.
Now, if you differentiate this with respect to theta, you get 5 secant tan,
Mm-hmm.
right? And the crossover then, you get 5 secant tan, that guy, right?
Mm-hmm.
So this becomes the square root of square this guy, you get 25 secant squared theta, take away 25. On the bottom, you get 5 cubed secant cubed theta. And then you get that guy, 5 secant theta, tan theta, d theta. Does that look what you got?
Yeah.
Okay. See if we can cut out some lines here. What does that top end up looking like? What does 25 secant squared take away 25 look like?
That's 5 tan theta.
Nailed it. So I could have cancelled earlier, but I'm not going to bother. We'll do it next line. Okay, let's do some carnage here, I hope. That secant will cancel out one of them and leave a square. That 5 and that 5 will cancel out with this guy and you'll still be left with a 5.
Yeah.
So we're looking at the integral of tan squared theta over 5 secant squared theta.
Mm-hmm.
What I'm now going to do is I'm going to turn everybody into sines and cosines. So what I've got is, well, let's take that 5 and stick it outside as a fifth. It's just getting in the way. That's sine squared over cos squared and 1 over cos squared. That's tan squared.
That's right.
That's secant. Now, what you might notice, I hope you notice that they cancel out. And what you're left with now There's a fifth. It's a secant square theta.
Yeah, that's what I got. I can't see your paper anymore. So.
You know, okay, let's see if I can figure out where the optimum place. That's the wrong way. If I
No.
go, can you
Okay.
see that?
Yeah, now I can see it.
Can you see my pen?
Yes.
Okay, so that's the place I should leave this damn thing. Okay, well, where should I go next? How am I going to get secant square theta?
Oh wait, that's sine. Sine's good.
What is it? Secant squared, not sine 2 theta, it's secant, sine squared. Oh, you're right. Sine square theta. Where am I going with sine square theta?
That would be like, is it called the half angle formula?
Yeah.
Yeah.
Well, it's double angle, half angle, whatever name you want to call it, but it's a half of 1 take away the cosine of 2 theta.
Uh-huh.
If I pull that half outside, it's 1/10, 1 take away the cosine of 2 theta, d theta, which gives me the integral of 1, which is theta. If you integrate a cosine, you get a positive sign. So that's negative the sine of 2 theta, because it doesn't change that. And what does the 2 theta give us?
A half.
So that's the answer, right?
Yeah.
In terms of theta. Did you get to here?
Yes.
Oh, you are cooking. You are not far away from the answer then. Because the only bit that's going to be left now is the triangle, which you use to get everybody back to x's. So x is 5 secant theta. So x over 5 is secant theta. And then I'm just going to turn it back upside down and call it cosine theta. And then I'm going to build my triangle. And I'm going to have an opposite and adjacent and hypotenuse. And in this world, a cosine is adjacent over hypotenuse, which makes this guy x squared take away 25. Why is that a good sign?
Because we started out with that at the top.
Right. So we know if we see that we've done the right thing, right? Now I need to get a theta. Well, I'm going to actually just use this guy or this guy. Well, let's use this guy. That makes theta the inverse cosine of 5 over x. You could have, and it's totally correct to have done it, you could have used this line here and said that theta was the inverse secant of x over 5, and that's the same thing. Okay. Now I need to get this piece and we're finished, right? Now this triangle only deals with thetas, right? It doesn't deal with 2 thetas. That means I have to figure out another way of writing the sine of 2 theta.
Which would be 2 sine theta cosine theta.
So negative a half of this guy becomes negative the sine of theta, cosine of theta. Right, negative a half of this gets you negative 1. Right? And sine becomes opposite over hypotenuse, which is this guy. Cosine is adjacent over hypotenuse, which is this guy. And that becomes that guy, which means we have that answer.
Okay. But
So
what I must have done wrong is with the 2 or something. I don't know what I did.
Right, but do you have, I mean, if you have your working, you should be able to say, okay, that's where it went wrong. Have you thought, did it look good up to here?
Yeah, it looked good up to there, and then I multiplied through the 1/10, and then I had a 1/20th and a 25 at the end because I didn't, when I went to do the sine of 2 theta, I didn't put in the -1/2. I just left that out for later. So that's where I went wrong because I had a
This guy went home without telling you, right?
yeah.
Yeah,
So I messed it up in there.
but not too bad. You were pretty much most of it.
Hmm.
Okay. So you had one last one, I think.
Yeah. It's the partial fraction.
Okay.
Number 9. It's the integral of y divided by y plus 2 and 5y minus 1.
Y plus 2, and what was the other one?
5y minus 1.
Did it have any limits to integration, like numbers? No, okay. So we're going to take this guy. I've got a gut feeling that it's just going to be a number mistake. I think you'll have done the process right, but you probably got a number screwed up. You know, it's a half, not 2, you know, that kind of thing. That's what I'm guessing. So we know that you split it into its 2 baby fractions called the partial fractions, right?
Right.
In this case, they are both single numbers, right? It's not like there was a y squared plus 1 in the bottom. This guy here, you multiply by 5y minus 1. And this guy here, you multiply by y plus 2. Does that look good?
Yeah.
Right, now, only the top row matters because the bottom row is the same. So I can now say y equals a lots of 5y minus 1 plus b, y add 2. And now we get to the choose thing, right?
Mm-hmm.
So it's going to be choose y equals. These are a bit easier because it doesn't matter which one you pick first or second, right? They both work. So give me a y value to choose.
-2.
Right. And if you pick -2, this guy is -2. This is a. 5 lots of -2 take away 1 is -11, and that's 0, which makes a positive 2/11. Okay, now we have our second and final choice. What value?
1.
That's where you went wrong then.
Oh wait, I picked 1/5.
Go, you didn't go wrong then. It's going to be messy, but we can live with it. 1/5 equals essentially a times 0, which is 0, plus b times 1/5 add 2. So 1/5 is going to be equal to, well, that's 11/5. And if you divide both sides by 11/5, you will eventually get Did you get 1/11?
Yeah.
Okay. You are going. Then I would have thought you would have made your mistake by now, but you haven't. So the integral of this guy is a over y plus 2, which is this ugly fraction, over y plus 2, plus 1/11 over 5 y minus 1 dy. Okay. If you integrate 1 over y plus 2, don't you just get the natural log of y plus 2? And then there's 2/11ths of them. So you're happy about that guy.
Mm-hmm.
This is where you're running short of places to make a mistake. So this is the next candidate for where your mistake is. There's an 11th there. 1 over 5y minus 1 is definitely the natural log of 5y minus 1 times something.
Oh. Is it
Is
gonna
that
be
the-
a fifth?
Yeah. Is
Okay.
that where you lost it?
Yeah.
Okay, now we know.
Okay, thank you.
Did you lose a 2.5 in the other question as well? I'm just wondering if it was the same kind of mistake in both cases.
And the sign one?
Yeah.
No.
Okay, so if it's different mistakes, so just be careful. If it was the same mistake, I might say to you, will you try and remember then it was 2x or 5x or 4 theta, that number generates a fraction when you integrate. So a 2 theta gets you a half and a 5 theta gets you a fifth, for instance. And I think that's us then.
Thank you.
Can I keep this as part of the video for other people so that they can see they can see it?
Sure.
Okay, thank you. Right then, bye bye. I'll see you on see you Monday.